Okay, I'm going to start the class now. Now is supposed to be lecture class, but I want to use this 1 hour lecture to discuss the tutorial. Okay, last 2 weeks I have asked you to do the tutorial 4. Okay, we didn't manage to discuss the solutions during the tutorial class. Okay, because the tutorial class I let you all try to solve the question, so no time to discuss the solution. Okay, so this 1 hour lecture class, I will discuss the solution, okay, for some of the questions. Okay, I see I still have time to cover for another topic in lecture, so I use this lecture class to discuss the solution. Okay, in tutorial 4, there are 4 questions that I ask you to try. Okay, I am not sure whether all of you have tried the 4 questions or not. Okay, but I will discuss a solution. Okay, for those who haven't complete all the questions, okay, you can refer to my answer here. But for those who have complete, okay, you can also give me your answer. Okay, I will try to check your answer and see whether it's correct or not. If you have any questions, okay. Okay, so the first questions that I will discuss today is question 2. Okay, question 2, there are 3 parts, part A, B, C. Okay, part A is to describe how good a floor planning can be achieved with the aid of diagram. Illustrate a good floor planning with input-output pad, macros, and routing placement. Okay, so for this one, the answer you can actually find from the lecture notes. Okay, or you can also check in other books, okay, books or any others website, relevant website to floor planning. Okay, so for this one, so what will be the answer? Okay, how a good floor planning can be achieved. Okay, I will directly show my answer here. You can check. Okay, my answer is not all correct. Okay, some may be not correct. Okay, and it's not all the answer is given. Okay, there is a better answer for the questions. Okay, but this is the answer that I have now. Okay, so the answer for this is a good floor planning can be achieved by meeting the following. Okay, having minimized numbers of the wire. Okay, and then here given minimize the total chip area and total length of wire. Okay, this is one of the answer. Okay, and also to make the routing phase easy, improve the performance by reducing the signal delay. Okay, this answer given have to explain. Okay, for example, okay, the total chip area and the total length of wire, okay, need to minimize in order to achieve a good floor planning. Okay, and also in a good floor planning, the length of not the length, the wire have to make it routable. Okay, easy to be route. Okay, and also the signal delays can be reduced. Okay, and with the signal delay, it can improve the performance. Okay, how these signal delays can be reduced? Okay, we can actually minimize the numbers of wire or the length of the wire. Okay, not minimize for the numbers of wire, maybe it's not minimize the numbers of wire for reducing the signal delay, but the length. Okay, but the length. Okay, so this is how we should explain. Okay, and then with the aid of diagram, illustrate a good floor planning. Okay, for this one, we need to give examples. Okay, by drawing a diagram. Okay, I just use back the one that is given in lecture notes. Okay, this is the diagram. Okay, this diagram is the floor plan. Okay, there are two floor plan here. One is a problematic floor plan, another one is better floor plan. Okay, these two floor plan we can compare. Okay, compare and then we can illustrate. Okay, what are the difference? Okay, so this one already given to you. Okay, you just need to revise back and then to know. Okay, what is it? The difference between these two floor plan. Okay, so to illustrate a good floor plan, so this one we can draw in this way. Okay, with the order of the macro, the arrangement of the macro. Okay, the arrangement of the macro is different. Okay, by minimize the use of the area. Okay, so you compare this and this one, the area for this one is minimized. Okay, and then the route signal, okay, are also organized, reorganized. Okay, okay, so here these are the two the explanation. Okay, for the two diagram. Okay, the problematic floor plan has a bed placement. Okay, bed placement. Okay, this bed placements means the bed placements of the macro. Okay. Okay, and bed placement causes routing congestions resulting in increase in circuit area and wiring. And longer wires are used. Okay, longer wire cause more capacitance, longer delay, higher dynamic power dissipation. Okay, this one is for this one. Okay. Okay, and the good placement is a good placement of the macro, okay, or cell. Okay, with good placements, the circuit area and wire decrease. Okay, and then also the wire is shorter. When wire is shorter, then less capacitance. Okay, when less capacitance, then shorter delay and less dynamic power dissipation. Okay, so part A, this is the answer. For part B, okay, part B is to determine the requirement to follow when placing the macro in a good floor plan. Okay, this is the requirement when placing the macro in a good floor plan. Okay, there are a few steps and rules have to follow when placing the macro. Okay, this one is the guideline also given to you in lecture notes. Okay, the guideline here mentions that the macro should be placed near to the boundary or edges. The macro should be placed according to their hierarchy, and the channel space should be proper. The macro pin should be accessible. Macro pin's orientation should correct or towards the core. Okay, and maximum space for the standard cells and routing. So for this one, okay, there is a figure here that can illustrate that. Okay, so this is a figure. Okay, you see these four figure here. These are the floor plan of a chip. Okay, floor plan of a chip. Okay, with the input output port. Okay, so the black color here is the input output pin, okay, or port. Okay, this is macro. Okay, the orange box is a macro. Okay, so here this is the macro to input output port fly line. Fly line is meant by this one, fly line. So this one according to the guideline, okay, it's not stated here. Okay, but if you refer to lecture notes or any other reference book, okay, so the placements of the macros to the input output pin, they should connect in a fly line. Okay, they can connect in a fly line. Okay, but that also based on certain conditions. Okay, we also need to make sure that the length of the wire should be minimized. Okay, and not very long. Okay, and also the macro placed at the core boundary. This is the core, not core. This is a macro that is placed at the boundary of the core. Okay, and this is the macros to macro fly line. Okay, and macro place place to each other. Okay, so this is the requirement. Okay, for part C briefly explain the purpose of power planning and routing in a floor plan. Okay, so for this one, this also has been discussed before. Okay, power planning is a step along with a floor plan in order to distribute power with proper power drop analysis across the design so that the entire design is getting power uniformly. It is called as pre-routing as the power network synthesis (PNS) is done before actual signal routing and clock routing. Okay, so after we place the macro and cell, okay, we also need to determine the power routing, power and ground routing, and also the routing for the signal. Okay, before the power routing is placed, so they must have this power planning, okay, and routing. Okay, so this mentions what is it about power planning. Okay, and then the purpose is to distribute the power from power pads to all elements of the chip, unified supplies of power with less voltage drop. Okay. Okay, so this is a very general one that I show to you. Okay. If you have other answer than this one, okay, is can also be considered correct. Okay, but I have to see how you explain it. Okay. Okay, so this is the answer for part 2 and not part 2, question 2. Okay, so now next questions will be question 5. Okay, question 5. Okay, question 5 is on calculations. Okay, consider a resistive load inverter circuit with the following. VDD equals to 1.2 volt, K prime equals to 102 microampere per voltage square, and the threshold voltage is a 0.48 volt. Load resistance is 20 kilo ohm, and the width over length is 4. Okay, width over length is the aspect ratio, it is 4. Okay, calculate the critical voltages of VOH, VOL, VIL, and VIH. Hence, determines the noise margin of the circuit. Okay, for this one, the answer already given to you. Okay, if you try these questions with the use of the formula that I discussed before, you will get the answer actually. If you cannot get the answer, then maybe your calculation is wrong, or maybe you miss some part. Okay, so for this one, I'm not sure whether you have any problem or not. Okay, I will just directly show how to get the answer for this one, so you can check. Okay, for some of you, if you cannot get, then you can check. Okay, so calculations of VOH. Okay, now we need to determine the critical voltages of VOH, VOL, VIL, and VIH. Okay, for VOH, okay, we straight away we know what is the values of VOH. It is output high. Okay, usually VOH is equals to the values of the supplies voltage VDD. Okay, so it will be 1.2 volt. Okay, VDD. You see VDD is 1.2 volt as well. Okay, and then for VOL, okay, VOL, there is a formula here. Okay, this is the formula. Okay, this formula you need to apply, and then you substitute all the values given for the parameter in this formula. Okay, after you substitute all the values, okay, you will get the answer 0.1977 volt. Okay, so if you find your answer is not correct, then you will have to recalculate again. Okay, with all the values that is a substitute in the formula. Okay. Okay, now it goes to the calculations of VIL. Okay, VIL is input law. Okay, the formula is different. Okay, the formula is equals to the threshold voltage plus 1 over Kn multiplied RL. Okay, so this formula, you can straight away use it to calculate the answer to get 0.6025 volt. Okay, remember that the value of Kn here, we need to calculate. Okay, the values given is for K prime N. Okay, it's not Kn. Okay, you see here, there is a difference here. This is K prime N. Okay, you cannot straight away use this value. No, cannot. You need to calculate. Okay, to calculate it, to calculate the K prime, okay, you need to apply the K prime and multiply with width over length. Okay, I mentioned to you before, okay, on this. Okay, now I mentioned again to help you to recall. Okay, so please make sure you remember this. Okay, so after you get the K prime, and not K prime, after you get the Kn, okay, Kn, then you can multiply with the RL, then you get 8.16. Okay. Okay, so now I goes to calculations of VIH. Okay, this formula, okay, is the formula for VIH. Okay, and then again, substitute all the values into this formula, then you will get this value. Okay, remember that this formula, all this formula that I show for VIH, VIL, and VOL, okay, are for resistive load inverter. Okay, it is for resistive load inverter. Okay, so after we get all the critical voltages, okay, then the noise margin can be determined. Okay, so this is the noise margin formula. Okay, noise margin has two. Okay, one is low noise margin, another one is high noise margin. Okay, low noise margin is defined as VIL minus VOL. Okay, so it is a 0.4048 volt. Okay, and then the high noise margin, Okay, it is 4.016 volt. Okay, if you get the values of VIH, VIL, and VOL and VOH correctly, okay, this you will get correctly. Okay, the noise margin. Okay, I see the answer here is actually not correct. Let me check again. Okay, I see something wrong here. Anyone can see? This is 4.016, 0.4048. Okay. Okay, if you get a different answer, okay, I think something wrong here. Let me check again. Okay, VOH here, you see here. VOH supposed to be 1.2. Here is 5. Okay, so my answer here is wrong. This answer is wrong. Okay, 4.016 is wrong. Okay, VOH as given in the question here is 1.2 volt. Okay, here VDD is 1.2. Okay, so 1.2 minus 0.9837 volt. Again, you need to calculate. The answer here is wrong. Okay, this is wrong. Okay, and then VIL is a 0.6025 minus 0.1977. Okay, looks like this is correct. This is correct. Okay, so all of you, you need to take note. Okay, my answer here is wrong. So you need to do the correction. This one. This is not correct. Okay, so you need to calculate yourself. Okay, so this one I think no more issue. Okay, just some of the correction. This correction must be made. Okay. Okay. Next is in part 2. Okay, is to draw the VTC of the resistive load inverter with appropriate label. Okay, so I have mentioned many times what is about what for VTC. Okay, VTC is voltage transfer characteristic. Okay, it is a graph. Okay, a graph that is plot with V out versus V in. Okay, so after you get all the critical voltages, you will need to draw out. Okay, you need to draw out. Okay, how to draw? Okay, it is not difficult. Okay, if you understand, you can easily draw it out. Because it should be like this. This is V out. This is V in. Okay, V in also got many voltage level. This is VDO, VIL. Okay, if I'm not mistaken, this is below threshold. Okay, and also VIH, and there is a VDD equals to VOH. Okay, here is VOH, and this is VOL. Okay, when we draw, we need to draw a curve. Okay, for this one, we need to label. Okay, VOH is 1.2 volt, VOL is 0.19. Okay, if 0.1977 we round it, it will be 0.2. Okay, suppose we need to use a 0.198. Okay, not 0.2. It's 0.2. Maybe not accurate. Okay, so this is 0.198. Okay, for VIL, this is 0.6025. VTO, what is the values of VTO? 0.4, 0.48. Okay, so as calculated, the input law is higher than the threshold voltage. So we need to redraw like this. VTO. This is VIL is 0.603. VIH is 0.9837. Okay, so this is VIL. So the slope is here, and also there is another slope here. Yeah. Okay, so the VTC should be like this. Okay, with all the labels of critical voltage. Okay, you must know how to solve this. Okay, how to draw and how to calculate. Okay, this type of question is very easy to score. Okay, make sure you know how to solve this question. Okay, and this is also one of the popular questions that will come up in final assessment. Okay, so make sure you understand how to solve this question. Okay, so this is all the answer for question 5. Okay, now I go to the next questions. Any further questions? Okay, you can let me know if you have any confusion here. Okay, I will go to next questions. If you still have any questions regarding on this, the answer for these questions, okay, you can ask me later. Okay, now is question 7. Okay, question 7. Given K prime N equals to 10 microampere per voltage square, the threshold voltage is equals to 2.1 volt and VOL is equals to 0.86. For the resistive load inverter draw in figure 2. Okay, so this is figure 2. This is a resistive load inverter. Okay, deduce and show which values of VRL is suitable to be used in this inverter if the allowable width over length ratio of the transistor is to range from 1 to 5. Assume the inverter can only sustain the maximum average DC power dissipations of 0.16 milliwatt. Okay, so for these questions, answer is not given. I want to check your answer. I want to know what is the answer you given for these questions. Okay, anyone who have solved this question, please can you give me your answer? Okay, I want to see among all of you, anyone can solve these questions. What is the values of RL? Okay, students indicate, all of you. Have you tried to solve these questions? Okay, never mind. You can let me know what is your answer. Okay, this one VIL is 1 or 1 to 5. Okay, you see here the width over length is from 1 to 5, right? Means the values of RL can range from this to this. Okay, if you want to determine, you have to consider another factor. Higher RL will have higher occupations of the area. This one have larger space, larger space. This I need to check again because I easy to get from. It's easy to mix up things. Okay, but for this one you have to check lecture notes. For the load resistance that is with higher value, they will occupy larger area. Okay, and okay, later I will show this one. I will show how to determine this. Okay, so for question 7, I see that some of you get the answer, just that you don't know whether your answer is correct or not. Okay, so I will straight away show the answer here. Okay, before I show the answer, I have this slide. I want to recall this. Okay, that is in chapter 5. Okay, to solve the question 7, you will have to refer to this one to understand. Okay, okay, so the DC power consumption is already given to you. Okay, the maximum. Okay, so you know the inverter circuit that you should calculate with the power dissipations must be lower than the maximum power dissipations. Then only we can consider that load resistance. Okay, okay. When we have the load resistance, we can calculate the power consumptions. Okay, okay. Okay, I mentioned this first. Later, I will explain in a more complete way. Okay, so how to choose RL? Okay, you see the RL here, range from large values to small value. Okay, and then the power dissipations also will be small, will be different. Okay, this higher RL, the power consumptions will be smaller. Lower RL, the power consumption is higher. And also we have to look into this V over L. Okay, when we consider which RL to choose, we not only see the power consumption, and also we have to determine which length over L is suitable. Okay, okay, if okay, let me. On the other hand, if the propagation of a large. Okay, you see here. Okay, power consumption increase significantly as the values of the load resistant RL is decreased and the V over L ratio is increased. Okay, okay, you see here, we want to get a low power consumption. Okay, so the load resistance that we choose must be not very small, and then the width over length also must be not very high. Okay, means maybe 1, 2, or 3. Okay, you use the width over length to calculate the RL. Okay, to determine the RL. Okay, so if you choose a largest load resistance, okay, then the width over length will be smaller, okay, and then the power consumption here will be smaller. Okay, so okay, so I go back to the solutions here. Okay, this one you need to refer. Okay, if you don't understand what I am talking here, okay, you refer to this note. Okay, and also the answer that I okay, later I will show the answer. Okay, so for your answer, if you want to know which one you should choose, you can refer to this one to know which one you should choose. Okay, based on what you can get from your answer. Okay. Chua Young, is it? Yongchuan, oh, Yongchuan or Chua? Yongchuan. Okay, Yongchuan, just now, what is the value? RL. When RL is? Okay. RL will be 94. 98.6. Okay, so, why the value is so big different? Okay, okay, never mind. Okay, we can check together because there can be a different method of doing it. Okay, when with our length, RL is 96 point. Oh, 98.465. Then it 83.9. Okay. This is in kilo ohm, is it? Okay. Okay, I see that your answer is quite different than mine here. Okay, so this power dissipations also you get. Okay, other students, I'm not sure your answer. Which one you get? Okay, I will check Yongchuan answer first. Okay, so for RL with 98.465 kilo ohm, okay, this will give a lower power consumption. Okay, give a lower power consumption, and then the width over length here is 1. Okay, so if you want to know which one you should choose choose this one. Okay, why is that? Because this RL will give a lower power consumption. Okay, and then the width over length is equals to 1, means the area that will be occupied is also smaller than this one. Okay, okay. Okay, the values of RL here, okay, this is my answer. Okay, this is Yongchuan answer. Okay, the values of RL is different. Okay, but the conclusions will be the same. Okay, the conclusions will be the same. What I mean here is the requirement of selecting the suitable RL will still be the same. Okay, how we should determine that? Okay, okay, so here, okay, this one given to you is actually similar. The reason is similar with the one that I showed you just now in the lecture notes. Okay, you can actually refer from there. Okay, the selections of this resistor value is in considerations of the area occupied by the resistor in the layout. Okay, 97.45. Okay, this is based from my answer. Will not cause a large occupied area in the chip if compared to a resistance having 194.9 kilo ohm, even though it is a larger average DC power dissipation. Okay, the average DC power dissipation. Okay. Okay, so so this one is based on the RL in the table here. Okay. Okay. Okay, since the width over length given is from 1 to 5, okay, we can actually determine other 5 load resistance. Okay, we can list out all. Okay, and then when we want to choose the RL, the suitable RL, we need to see the power consumptions. Among all, these two are the lowest one. Okay, these two are the lowest one. And then when we choose this, the RL with lowest power consumptions, we also have to see the width over length. Okay. So width over length, larger width over length means that larger area will be occupied, right? Is it? From what I understand, should be in this way. Okay, chip area occupied by the resistive will depend on 2. Okay, we may choose a small width over length ratio and a large load resistor. Okay, so okay, my answer here, choose is the width over length with 2. Okay. Okay, so this one should be 194.90. Okay, so should choose this one. Okay, this one. Okay, if you use different method to get the RL, the values of RL you get will be different. Okay, but the one you should choose should be based on the lowest power consumptions and small width over length. Okay, this one you should take note. Okay, clear? Okay, so these questions done. I know now I goes to question 8. Okay. Question 8 is about the resistive load inverter is studied to occupy a larger chip area with a diffuse resistor as the load in the inverter layout if compared with enhancement type load inverter. Justify the reason. Okay, this one not difficult. Okay, the answer can also get from the lecture notes, okay, or from the reference book, okay, that is recommended. Okay, so for this one, okay, this is the answer. Okay, I will go a quick one. Okay, I see now the time is not enough. Okay, I have less than 10 minutes. Okay, so the answer is this. The resistor of the diffuse resistor is determined by the doping density of the diffusion region, okay, and the dimension. Practical values of the diffusion region with a sheet resistance range between 20 to 100 ohm. Consequently, a large length to width ratio should be required to achieve resistor values on the orders of tens to hundreds of kilo ohm. Okay. Uh, okay. Now it's talking about a resistive load inverter. Okay. You know the schematic diagram of a resistive load inverter. In layout diagram of a resistive load inverter, it is like this. Okay, it look like this. And then for the resistor, the load resistor in layout, we call it as a diffuse resistor. Okay, we call diffuse resistor. And then this resistor is actually constructed and determined by the doping, okay, by the type of the dopant, and then the doping density, okay, on this diffusion region, okay, and as well as the dimension, okay. And then the shape of the diffuse resistor here is looks like this. We call this shape is a serpentine type shape, okay. Okay, so this, if you compare with another resistor that using different fabrications technology, okay, this diffuse resistor has a seem to occupy a larger area. Okay, when it occupy a larger area means that it occupy a larger chip area. Okay, uh, okay, this the large area is occupied when it is being compared, when it is compared with the enhancement type load inverter. Okay, so this should be the explanation, okay, based on the comparison. Okay, okay, in enhancement type inverter, okay, the area occupied is a smaller, okay. One is smaller because MOSFET, okay, MOSFET is used as a load device instead of resistor, okay. And then this enhancement type load inverter, okay, with the MOSFET as the load, okay, the silicon area occupied by by the transistor is usually smaller than that occupied by a comparable resistive load. Okay, and then this enhancement type load inverter can be designed to have better overall performance. Okay. Okay, so this is the answer for question 8. So that is all the discussions for all the answer. Okay. Okay, for other questions, there are a few more questions here. Okay, I actually want to discuss the questions for this dynamic logic circuit. Okay, but I didn't have time to cover this. Okay, maybe in the next class, okay, in Wednesday. Okay, Wednesday I will discuss, I will continue with this, okay, with these questions. Okay, for other questions, all these questions that I have not discussed with you about the CMOS inverter and resistive load inverter, okay, all these questions, okay, is not difficult. Okay, I hope that when you do the revisions, you can try all the questions. Okay, that's for today. Okay, any question from you? No. Okay. If no questions, then I think we can dismiss class. Okay, before we dismiss, let me check again your attendance. 7, 20. Okay, Sharon already take attendance. Okay, students in Google Meet. Okay, suppose there are 24 students here. Oh, you are in the Google Meet. Huh? Oh, you're not in. Okay. So if I minus 3, okay, there's 24 students. Okay, the form I get is 23, means one student haven't filled up the form. Who are? Can anyone help to check? And I'm trying to see. Okay, now 26. Okay, 26. Just now I see wrongly, is it? Okay, now 26 means okay already. No issue on the number here. Just now who left? My presentation. Oh yeah, correct. My presentations and my 2 laptop here, 3, correct. Okay, now no problem. Okay, we can dismiss class now. Thank you. Okay, another group should stay back. Okay, we have a tutorial in the next class.